Okay, welcome back everyone. Today we are going to get into our next row of topics. So remember that we have introduced the theory of thermoconduction or thermoconductivity and diffusion or diffusivity. And we actually introduced the most important concept, which is the combined energy or combined mass flux vector. Today we are going to introduce a new topic, which is the shell balance. We're going to start with shell energy balance, looking at temperature distributions in solid and laminar flow. And throughout this section, we're going to be using the combined energy flux vector to do our analysis. Okay, so and also in this chapter, mostly we're going to be dealing with problems that are under steady state. Okay, so we know that under steady state, there would be no accumulation. So at steady state, we know that the rate of energy going into a particular system, so say rate of energy in minus rate of energy out would equal to the rate of energy production or consumption. Either way you would like to state that. Production. Okay, so if we write in a more general format, basically we know that the rate of energy accumulation would equal to the rate of energy in minus the rate of energy out plus the rate of energy production minus the rate of energy consumption. Okay, so let's write the more general format for you just to make it more general, right? So more general, let's just write it down. More general, we would write rate of energy accumulation equals to rate of energy in minus rate of energy out plus rate of energy produced, energy production minus rate of energy consumption. And typically, if the system is at steady state, then we can already say that the left-hand side is going to be 0. So at steady state, there would be no accumulation. So let's say at steady state. So all the left add together should be 0. Okay, so I believe that you all have this basic concept already have that foundation, right? So throughout the section, we're going to be using a number of different examples just to show you how we can utilize the technique of shell energy balance. So let's get into our first example. So example 1. Okay, so this is a example actually quite often used not for chemi people, but actually more often for mechanical engineers, right? Think of the moving parts in a motor or in a car, right? So in a car, you might have this situation like this, right? Let's say you have basically 2 coaxial cylinders. So let's draw, you have one cylinder and you have another cylinder that are coaxial. maybe draw this better. You have one cylinder. Maybe I can use I can use this real cool stuff. So that's your first cylinder. And then you have a second cylinder. Great. So and then basically between the cylinders we have a layer of Newtonian fluids. So let's try to color that. Maybe just with a blue pen would work. So let's try to color this. So within the two cylinders we have this Newtonian fluid. Okay, so you have a Newtonian, should be capital, Newtonian fluid between two coaxial cylinder. So a good example of this would be like motor oils. Motor and motor oils. Okay, and we can define the inner diameter. So the inner cylinder has a radius of r, and the outer cylinder has a radius of capital R. And then we have the thickness of the liquid layer here. Let's call the thickness being B. Okay, so what's going to happen here is that we are going to have the outer cylinder having an angular velocity of omega. So it's going to be rotating at an angular velocity omega. So omega would be our angular velocity. Okay, so what's going to happen in the system is that as our outer cylinder is rotating, basically the cylinder is going to bring a motion about the fluid inside, also rotating, and you can think them as layers of liquid on top of each other. So the liquid layer that are closer to the outer cylinder is going to rub against the layer of liquid closer to the inside cylinder. Okay, and so to put that into context as words, we'll just write down what's going to happen. So first, as the outer cylinder rotates, each cylindrical shell of fluid will rub against and adjacent shell of fluid. Okay, and that means what's going to happen is that there's going to be friction between each layer of fluid. Okay, so you're going to have friction between each layer of fluid, and when they are rubbed against each other, that is going to produce heat. So this is why we call this a viscous heating source. Produce heat. Okay, and in other words, that's a transformation of mechanical energy to thermal energy, to thermal heat. Okay, and this is why we need to use the combined energy flux vector. Sorry. The combined energy flux vector. Okay. So before we go further, let's kind of review what's going on here. So what's happening here is that the outer cylinder, when the outer cylinder is rotating at an angular velocity, basically you can think of each shell of liquid is going to rub against inside, the liquid layer inside, right? So if you have a liquid layer here, and then basically it's going to drag the liquid layer within, right? It's going to drag and propagate down, and the velocity difference between each layer is going to be caused by friction. So you're going to have friction at each interfaces, and the friction will give you heat. Okay, so this is why this is a viscous heat source. And our question is, can we figure out the temperature distribution inside that liquid layer? Okay? So, to make our lives easier, let's make a simple assumption. Let's say that, what if the liquid layer is very thin? So mathematically, what if the liquid layer thickness B is much, much smaller than the radius of the outer cylinder? If that is the case, then we can view the fluids, or the fluid being sandwiched between two parallel slabs. Okay, and the essence there is that what we can do is we're going to basically neglect the curvature effect. Neglect curvature effects, and then we can go to the simple Cartesian coordinates. Okay, so basically the system now looks like the following. It looks more like we have one plate or one slab on the top, a second slab at the bottom, and the top slab is moving at a velocity vz. So let's define this as x and z. Okay, and you can envision that you would expect a velocity profile that looks somewhat like this. Okay, so the top surface is moving, so this is our top surface. And the Vz here equals to what? Equals to basically Vb equals to r omega. So the radius times the angular velocity. Okay? And so let's kind of rewrite this to make it clear. So the top surface is moving at a velocity v sub b, which equals to the radius of the cylinder, outer cylinder, times its angular velocity. And we would have a linear profile of the velocity distribution within that liquid layer, and it would be proportional to the upper plate velocity times x over the thickness of the liquid layer. Okay, so that gives us our first simplification of the system. So we are transferring from a cylindrical coordinates having curvature effects down to a very simple one-dimensional problem using Cartesian coordinates. Good. Let's continue. So here is the part where the shell energy balance should come into play, right? So again, we're going to try to make a shell. We're going to define a shell of liquid and try to perform an energy balance throughout that shell. So let's call it shell energy balance. And we're going to use the combined energy flux vector. The combined energy flux vector. Okay, so before we move further, we need to first figure out what's the most appropriate way to define the shell. So let's take a look here. So let's draw it in a more 3D fashion to show you what I mean. So let's say we have upper plate that looks like this. And a lower plate. Okay, and we can define our coordinates, x and z. And let's try to copy this so we can make things a little bit quicker. So let's copy that and paste it here. And we will discuss both cases. So the first question for us is, how do we define that shell, that control volume, right? And how do we do a balance over that, right? So there are two selections naturally you can think of, right? So one type of shell would be like this, that you have a very small distance in the z direction. So this is one way you can define a shell, and then you have another way to define your shell would be parallel to the moving plates, right? So let's first draw both cases down and see what's going to happen. Okay, so in the first type of shell on the left-hand side, you would be defining z and z plus delta z. So you have a very, very small thickness or very thin thickness in the z direction, but you have no other type of restraints, right? So you have you can have the height being b and the width being w. Okay, and for this part you have the other way. You have your delta x, and you have the width w and the length L. Okay, so now let's take a look on how we should define or how we perform the energy balance here, right? So if you define the shell as the left-hand side, or on the left-hand part, sorry, on the left, you'll be assuming that your energy flux comes in this direction and goes out this direction. Okay. And if you're looking at the right-hand side, you may be defining your flux going from inward from the top and coming out from the bottom. And let's take a look at what's going to be different here, right? So let's try to proceed from the left-hand part first. So at steady state, you have in minus out equals to 0. Okay? And you're going to use the combined energy flux vector to do this. So what do you have here? You have the combined energy flux vector coming in, and you're going to have it times the, this is coming in at z times the area, which is W times B, minus EZ at Z plus delta Z WB equals to 0. Okay, and what you see here is that the cross-sectional area would all be the same, right? So what you gear here, if you divide all, let's divide all. Divide all by W, B, and delta Z. Then what you get is the following. You have EZ at Z minus EZ and Z plus delta Z over delta Z equals to 0. So you have d EZ over dz equal to 0. So you have E sub z equals to a constant C1. Okay. And let's do the same thing on the right-hand side. So again, at steady state, we have E in the x direction now. Ex at x times WL minus Ex going out at x plus delta x times WL equals to 0. Again, we are going to divide all by WL and delta x. So we get Ex at x minus Ex at x plus delta x over delta x equals to 0. So you have d Ex over dx equals to 0. So you have the same type of conclusion. Ex now equals to some constant C1. Okay, so let's try to continue, right? So remember, if we analyze the problem, how would you expect the energy to be transferred? Should it be transferred in the z direction, or should it be transferred in the x direction, right? So if we continue our discussion, we can still proceed with both directions, right? So let's take a look at what EZ is. So let's kind of review the combined energy flux vector. So EZ would be what? Would be the convective energy transport, rho v square times rho u times vz plus q, which is the flux, and plus work. So pi times dot product with velocity in the z direction. So remember, we have what? The first part is convective energy transport. The one Q is heat, and this is the mechanical work, right? Okay, so let's proceed now, right? So you would see that if we continue to analyze this part, we have 1/2 rho v squared plus rho u prime vz plus q plus, we can refine it to h now, sorry, so we can do this to h, pressure term goes in, and then we can use the shear stress now in the z direction. And if we keep on analyzing this, we can see that if you look at the mechanical stress part, tau v in the z direction equals to what? Equals to tau xx times vx. I'm sorry, it should be tau zx vx plus tau zy vy plus tau zz and vz. And that equals to what? That equals to basically, if we analyze this, there's no velocity in the x and y component, so we're left with the last term here, and that equals to negative viscosity times what? Times partial vz partial x plus partial vx partial z times vz. I'm sorry, I would like to make a correction. So tau zz is the following. So there's no shear part, so tau zz is basically partial vz partial z plus partial vz partial z times vz. And you can know that from our statement here, if we come back to our initial, vz here is not a function of z actually, so it doesn't changes with z. So partial vz partial z is also 0. Is also 0. So basically, there's actually no mechanical works associated in the z direction. And there's obviously no changes, so this is going to be 0. And if you look at the convective energy transport at z and at z plus delta z, there should be no difference. So basically, Ez is going to be the same at z and z plus delta z. So obviously there's going to be no heat associated. So Q would be also 0. Okay, so that's why after doing the analysis here, we can know that, let me erase this because I'm going to use the other part for the x direction. We can know that we can do our energy balance with a shell defined like the left hand side, but that's going to lead us to nothing because there's no energy transport actually occurring in the z direction. But the energy transport should be happening in the x direction because you're having variations of velocity in the x direction, which gives you the friction and heat coming out, right? So let's focus our attention on the right hand side now. So again, we can use the same tactic and techniques. We'll say that, let me bring this a little bit here. Sorry, some technical issues. Not sure why this is showing up. Give me a second. Okay, that should do it. Okay, so if we again expand the combined energy flux vector in the x direction, we have E sub x equals to what? Equals to the convective transport part, so that's 1/2 rho v squared plus rho u cap times vx plus q plus the work in the x direction. Okay, and we can rewrite that in the form using shear stress and the enthalpy. So rho v squared plus rho h vx plus q plus tau vx. Now we know that there is no velocity component in the x direction. So there is no convective energy transport in the x direction. And if we look further into the shear stress, the work associated in the x direction, this would equal to tau xx vx plus tau xy vy plus tau x z vz. Again, no vx, no vy, but now we have the shear stress, so it's negative mu times partial vz partial x plus partial vx partial z times vz. Now vx is 0, but actually now we do have this term, right? Because we know vz is a function of x. So this equals to what? This equals to negative mu partial vz partial x times vz. So your combined energy flux vector would be what? E sub x now equals to negative k dt dx, which is the heat conduction term, minus negative or minus mu partial vz partial x times vz. Now we can now proceed, right? So remember, from shell balance, so we're going to proceed down here. So from shell balance, we know that the combined energy flux vector is a constant, equals to some constant C1, and also equal to negative k dt dx minus mu partial v z partial x vz. And we already know that vz equals to vb times x over b. So that means partial vz partial x equals to vb over b. And so we can plug this back here to get what? To get C1 equals to k minus k minus k dt dx minus mu vb square, over b square. B square times x. Okay? or we can rewrite this such that we omit the negative sign. So we can write this as k times dt dx plus mu vb squared over b squared x equals to some constant c1. So basically the second term here is the rate of viscous heat production. So you can see that if you have a higher temperature, if you have a higher velocity of VB, meaning that you are having a faster spinning outer cylinder, you're going to generate more heat, and that's going to reflect on the temperature distribution. Okay, so now we just need to do what? We just need to integrate this ODE now, right? So let's try to do that. It's fairly simple. So integrate ODE. So let's try to do that. So we have k t prime plus mu times v sub b over b squared x plus some constant c1 equals to 0. And we can also write this as t prime, if we divide all by k, mu over k times v sub b over b squared x plus c1 over k equals to 0. Okay, and we can call this a new c1 prime, so we can write dt dx equals to negative mu over k times vb over b squared x minus some c1 prime. So dt equals to this whole thing, mu over k vb squared over b squared x minus c1 prime dx. Now we integrate both sides. Integrate both sides. We get t equals to negative 1 over 2 mu over k vb over b squared x squared minus c1 prime x plus c2. Okay, now we need to apply the boundary conditions. So what are our boundary conditions? Boundary conditions. Now let's say that our boundary conditions is the following. At x equals to 0, we have t equal to t naught. And when x equals to b, we have t equals to t sub b. And if that's the case, if so, for t naught not equal to t sub b, we have c2 will equal to t naught. And t sub b would equal to negative 1 over 2 mu over k vb over b squared times b squared minus c1 prime b plus t naught. So b squared cancels out here, so we get c1 prime equals to T naught minus TB minus mu over 2k times VB square times b to the negative 1. So finally we get the temperature profile now. So we get T equals to negative mu over 2k times VB over B square X square minus this big chunk of stuff minus mu over 2k over let's see, VB square times X over B plus T naught. Okay, and a couple of rearrangement steps gives us the last type of cleaner formation of the solution. Equals to negative 1 over 2 times mu over k times TB minus T naught VB square times X over B square plus 1 minus 1 plus mu over 2k times VB square over TB minus T naught X over B X over B. Okay, so in the final format, you can see that there is a number that keeps showing up, which is what? Which is this thing here in the bracket. This is called the Brinkman number. So Brinkman number. It's a dimensionless number. It's defined as mu VB square over k times TB minus T naught. And it's a measure of importance of viscous dissipation term. Okay, so if we write that down, so Brinkman number is abbreviated as BR. We can again rewrite our equation, the temperature profile, as the following. TB minus T naught equals to 1/2 the Brinkman number times X over B times 1 minus X over B plus X over B. And this is a hyperbolic function. Hyperbolic function. So what that means actually is that your temperature profile might look like this, right? So you have an upper plate and a lower plate, and this is moving at VB, and you already have a velocity distribution that looks like this. But your temperature profile may look different. So you may have TB here. If you have T naught here, you actually have the highest temperature somewhere in between. And that's because you are generating heat due to the friction between different layers of liquids. Okay, and this temperature is important because, let's say if today you are designing some lubricants for this motor, you want to know that temperature. What if the temperature is so high that it makes your lubricant decompose? That's not going to be good, right? So this is why we want to know this, because this is actually the highest temperature. You know, I would say like you would have higher temperature than the boundary conditions. Mark there. Okay, so then now what if, simple case, what if TB equals to T naught? Or TB equals to T naught, then we have something a little bit simpler. So we have T minus T naught over T naught equals to 1/2 mu VB squared over KT naught times x over b times 1 minus x over b. Okay, so this is finishing the solution part, and before we go into our next example, I would like to spend a little bit more time discussing about each terms happening here. Okay, so let's take a look at the viscous heating term again. So the viscous heating term. We have SV equal to mu times VB squared over B squared, right? And basically, this refers to the rate of work. And it equals to what? Equals to force acting on the upper plate. Upper plate times the velocity of the plate. So it actually equals to negative tau x z times WL times VB. And it can actually be, think of what? The energy addition per volume. So that equals to what? The rate of work divided by WLB. So that equals to what? Equals to tau xz times VB over B equals to mu VB squared over B squared equals to S. Okay, so you can think of this in two ways, right? So the viscous heating term is the rate of work and equals the force acting on the upper plate times the velocity of the plate. And it can also be viewed as the energy addition per volume, which is the rate of work divided by the volume. Okay. Now finally, let's make some closing remarks for this particular example. So let's call it just notes. And let's move it back a little bit. So notes. So viscous heating is actually not important in most problems. In most problems. But if dV dx is large, it cannot be neglected. Some examples are also relevant, right? If you have a bullet going through the channel inside your rifle or your gun, and that's going to have a dramatic, huge dV dx, right? So you're going to have a lot of heat generated due to the friction between the bullet and the lubricant. Again, if your lubricant gets decomposed, then they become what? They become like carbon materials, and it might plug your rifle, and that's going to cause danger, right? So if you have a really huge velocity a gradient, then viscous heating cannot be neglected, okay? So some examples are, one would be flow of lubricant between rapidly moving objects. Or parts, whatever you call that. And then what if another way that this can be important is when your liquid or the fluid is very viscous, right? So that's like flow of molten polymer. Molten polymers through dyes in high-speed extrusion. Or flow of highly viscous fluids at high velocity. Okay, or another thing that's really relevant would be flow of air in boundary layer. In boundary layer near Earth satellite. Or rocket entering the atmosphere. It will be more and more important in future aspects, like think about SpaceX, right? SpaceX is always going to the outer atmosphere and returning it, and that means that it needs to consider that friction of air at the boundary layer when it's re-entering Earth's atmosphere. And how do you know the heat that's going to generate it? And that means the material you're going to use needs to be able to stand that type of high temperature.